Today we're going to continue our discussion on techniques for evaluating limits. The first discussion I want to have today is about one-sided limits. So here's the notation that we are going to use. You'll see it looks very similar, except we have either a plus or a minus sign next to our C value. So if we're talking about the limit from the left, we're talking about the limit as x approaches C from the negative side as we're coming from the left, okay? So we're basically just following the graph only on the left side to see what function value we are approaching. All right, and then if we look at the limit from the right, the notation is the limit as x approaches C from the positive side, or the right side, and we are looking at graphically what function value are we approaching from the right side of C. Okay, so with one-sided limits, we do not have to follow both sides. We can just follow either the right or the left based on the notation. Now, when we were discussing when a limit does not exist, we discussed that if our left and right sides are approaching different values, then the limit does not exist. So that leads us to the existence of a limit. We've talked about what a limit is, but we've never actually defined for sure when it happens. We've only defined when it doesn't happen. So now that we know what a left-hand limit and a right-hand limit are, then we can finally define the existence of a limit. So if f is a function and C and L are real numbers, then our limit as x approaches C of f of x equals L. So basically this is saying our limit exists if and only if the right and left hand limits exist and are the same. Okay, so as long as the right hand and the left hand limits are the same, then the limit exists and is that value. Okay, I would like everybody to get their calculators out, and I want you to graph y equals the absolute value of x over x. Okay, you should get a graph that looks something like this. Okay, let's talk about why this makes sense. All right, if we have numbers plugged in that are positive, okay, first of all, the numerator is always going to be positive, and the numerator and denominator are always going to be the same thing. So we're always going to get 1. Now, when we look at the left side, when we plug in negative values, our numerator is still going to be positive, but our denominator is going to be the same value but negative, and that will always divide to be negative 1. Okay, so now what do you think we are going to get for this graph? Okay, if you plug this into your calculator, we are going to get something similar to what we had in our last graph, but it's going to be at 3 and negative 3 because our numbers are going to divide that way. Okay, you need to remember what this graph looks like so you can picture it, and we're going to use this graph to evaluate limits. Okay, so let's look at this first example. Okay, we always want to use direct substitution if we can, and if it does not work, then we need to look at our other techniques. So in this first example, if I were to try to use direct substitution, it's not going to work. Our denominator is going to be 0, and that's not okay. This is not a rational function that we're used to seeing. Okay, we don't have polynomial over polynomial, and we don't have that radical we can use the rationalizing technique with. So what we can do is we can look at the right and left hand limits. Okay, if they are the same, then that's what our limit is. So first, I want you to picture the graph. We just got through talking about this. So we know our graph is going to look like this. Okay, now we first want to look at the left-hand limit. So the limit as x approaches 0, but we're going to put a little negative sign there because we're looking at it from the left, of 2x absolute value of 2x over x. Okay, now I do want to see this work on your homework, on your test. Okay, what is the left-hand limit as x approaches 0 of the absolute value of 2x over x? So if we look at this from the left, we see that it is approaching -2. Okay. Now, if we look at the limit as x approaches 0 from the right side of our function, we see that that is approaching a +2. Since these two do not match, then we say that our limit does not exist. Okay. Now, if we go over here to our second example, okay, I don't want you to forget that we always need to start out with direct substitution if we can. So first of all, is -2 going to make our denominator 0? No. So all we have to do is direct substitution. And what do we get? 1/8. Where right and left hand limits really are the most beneficial is when we have a piecewise function like we do in these two examples. You can see that in this first example, our graph breaks at 1. Okay, so we have a piece of a line to the left of 1 and a piece of a parabola to the right of 1. So in order for us to figure out if our limit exists, then we are going to have to look at a right-hand limit and a left-hand limit since we are evaluating the limit at the break in our graph. Okay, now two things can happen. Either we have a complete break and the right and left-hand limits are going to be different, or these two pieces are going to meet up at a coordinate and our limit will actually exist. Okay, so the only reason we are taking a right and left hand limit is because we're evaluating the limit where we have a break in the graph. Otherwise, we would not need to break it up into right hand and left hand. So first of all, let's look at the limit as x approaches 1 from the left side, okay, of our function. Now, the domain restriction for the first function is that x is less than 1. So that is the function we are going to use to evaluate our limit for the left-hand side. So if we plug in 1 on the left of 1, we get 4 minus 1, which is 3. Now, if we look at the limit as x approaches 1 from the positive side of our function, okay, well, our domain restriction for the second function is x is greater than 1. Okay, so as we approach 1 from the right side, we are moving along this parabola. So if we use direct substitution with the parabola, we get 4 times 1 minus 1 squared, which is also 3. Since our right hand and left hand limits are the same, then we can say that our limit is that value, which is 3. Okay, so I just want to take a look at this graph so you can get a visualization to what's going on. Okay, so first of all, we start our line of y equals 4 minus x at 1 and to the left of 1. But notice how there's no equal sign, so we have a hole there. So at 1, we would plug it in, and we would get 3. All right, and then this is the line 4 minus x. Okay, so we have that y-intercept of 4, and we have a slope of -1. So there's that piece of the line. Then we have the piece of the parabola, 4x minus x squared, but only when x is bigger than 1. So we still have a hole at x is 1, which when we evaluate at 1, we get 3. When we evaluate at 2, we get 4. And at 3, we get 3. And so we have that piece of the parabola. So you can see, even though it's a piecewise function, we're meeting at that point 1, 3. And when we evaluate the limit as x approaches 1, the right and the left side are approaching the same function value, and the limit exists and is 3. Okay, I'd like to come back to this second example. Okay, you see we have a piecewise function with 3 pieces, and I want to evaluate the limit as x approaches 2. So I see that right here we have a break in the graph at x is 2. So is it a complete break, or are the 2 pieces going to meet up? Okay, that's going to determine whether a limit exists or not. So let's find out. So the limit as x approaches 2 from the left side of our function means we are going to use this piece of the domain right here, because this is saying x is between 1 and 2, or equal to, okay? So when we evaluate that limit, we see our function is just 10, and so we're following along that function y equals 10. Now, from the right side, the limit as x approaches 2 from the right side. When we look at the domain restrictions, I see that we are to the right of 2 right here. And so when we evaluate that limit, we are going to have 12. So I see that our right-hand limit and our left-hand limit are different, so our limit does not exist. Okay, so maybe some of you recognized this function, but here is the graph of our function, and you see we have a piece of that stair-step function that we worked with back first semester, and you can see at 2 we have a complete break in the graph where our 2 different pieces don't meet up. Our right-hand and left-hand limit are not the same, and so our limit does not exist. Okay, so the last thing I would like to discuss is what we call the difference quotient, okay? We are going to take the limit of the difference quotient, which I will warn you right now is going to involve some algebra, okay? So the limit of the difference quotient is this right here. The limit as h approaches 0 of f of x plus h minus f of x all over h. Now, first of all, you'll notice that we're taking the limit as h approaches 0, and we have h in the denominator, so we will have to use some of our algebraic techniques to be able to evaluate these limits. Okay? These limits of the difference quotients are very important. We will be using them to evaluate derivatives or introduce derivatives here on Friday. So this is one of the most important limits you are going to evaluate. So you need to make sure that you practice these and you can work with the algebra. Okay, we are going to do an example. I have right here for us an example. We're going to evaluate the limit of the difference quotient when our function is x squared minus 1. Okay, so here I have our example, and I have written the difference quotient for us. And we're going to go ahead and evaluate this. Now remember, until you actually use direct substitution to evaluate the limit, you must write the limit as h approaches 0. Okay, so first of all, we have the limit as h approaches 0 of f of x plus h. That means plug x plus h into your function wherever there's an x. So since x squared minus 1 is our function, f of x plus h is, here's my x squared, and then we have minus 1. So x plus h squared minus 1. Then we are going to subtract f of x. Now, since I have more than one term, I'm going to go ahead and put it in parentheses so I don't lose out on any negatives, all over h. Now you see we cannot use direct substitution right now. We're going to have to do some algebra. So I'm going to go ahead and work with our numerator here. So we're still working with the limit. We have not evaluated it yet. If we go ahead and multiply out x plus h, the quantity squared, we have x squared plus 2xh plus h squared. And then we have our minus 1. And I'm going to go ahead and distribute that negative through, so we have minus x squared plus 1. All right. Now I see that my x squareds will cancel out, as well as my minus and positive 1. So now I'm left with the limit as h approaches 0 of 2xh plus h squared all over h. And what do you notice about our numerator? Hopefully, you all have noticed that there is an h in common with my terms in the numerator. So we can go ahead and factor those out, okay, which causes those to cancel. So we are finally down to the limit as h approaches 0 of 2x plus h. Now, please remember, this limit we are evaluating is when h goes to 0. So that is the value we're substituting in for. That is the variable we need to substitute in for. 0 needs to go in for h. So when I plug 0 in for h, we are left with 2x. When we take the limit of the difference quotient, you will get either a constant or terms with the variable x. Okay, so do not panic that we have 2x as our limit. Okay, that should happen, and it is okay if you get x's when you evaluate your limit of the difference quotient. Here is your homework assignment. Please use your time wisely. Work together and compare answers. Please make sure you look at those difference quotient problems and work on your algebra. Okay, tomorrow we will discuss any issues you had on last night's homework that you didn't get answered in class, and then any issues you had on this homework. So please use your time wisely and get to work.
Made with Doodlecast Pro.